Good morning. Today we are going to prepare an input file to model a simply supported concrete slab. And we start at this stage where we have already defined 4 points, 4 lines and 1 surface. And watch the normal of the surface is pointing up here. It is depending on the direction, the tangent of the first line which defined the surface. So we can remove the labels and also the normal and the tangent. We have also prepared a TSH file. Here is the geometry of the file in which we have computed the temperature. We see that we have 2 materials. We have 20 centimeters of concrete and 2 centimeters of an insulating material. And here is the TSH file from -12 centimeters to +10 centimeters. But the structural part of the slab will be from -10 centimeters to +10 centimeters. So we can close this file. Let's come back here. Now we have to introduce the physical groups. First, we add the supports, and we introduce a physical group which is a curve. We give it as a name short supports with an S because there will be 2 short supports, that one and that one, type E. And the block constraints are F0 in the vertical direction, and we also fix the rotation in the Y direction. F0 here, and that's it. So add update, I click twice. Okay. Now I add another physical group based on curves, and it will be called long supports. And there are 2 of them, one here and one here, type E. And the constraints now are again in the vertical direction, but with regard to rotation, I don't fix the rotation with respect to Y, but the rotation with respect to the X axis. Add update. Now I add a constraint on a point, so I want to create a physical group based on point, which I will call point support without any S because there will be only one point. This is that point, type E, and here I want to fix the rigid body movement of the slab. So in the direction X, that's F0, in the direction Y, that's F0. I don't need to fix the vertical direction because at this point the vertical displacement is fixed by the long supports and by the long supports, by the way, and the rotation is fixed around the vertical Z axis. Add update, so I can close. And now I can check my blocks and I see, well, the color is not very appropriate, but if you look carefully or if you are smart enough to change the colors, you'll see that we have what we wanted. The next physical group I have to create is the one that deals with the surface. And the name of that surface will be very simply slab. I select the surface here and I can type E. Now I start defining different properties of that physical group. I will start by the new material definition, and that will be the material of the slab. So it's not carbon steel, it's more or less concrete, siliceous concrete, ETC2D, why not? Poisson ratio would be 0.2. Let's assume that the compressive strength is 40 megapascal, and let's put a tensile strength of, I don't know, 2 megapascal. The other parameters are okay. I give a name, that's concrete, so I call it concrete M2. to remind me that this is concrete and that this is a material. Add update twice, and now I see the concrete appearing here in the list of the material names choice. So this material has been defined. It has not yet been allocated. So I will create a new rebar material that's not a non-load bearing material, that's carbon steel. It's not steel EC3, it's steel EC2 most likely. Okay, the parameters are okay. I just changed the name and I call it steel M. And update twice. Now I can come and start from the top of the list. I don't have constraint. I have loads, of course, with the function fload. And for example, in the vertical direction, that would be minus 6,000 Newton per square meter. Add update. I will not put masses because I will make a static calculation to be a little bit faster. I have to define the material of the shell. And here I have different informations to give. The file name, that's the name of the TSH file. And the name was shell.th.tsh. I have to give here the thickness of the structural part of the file. That's 0.20 centimeter. And the name of the material which makes the matrix of the shell, and that was concrete M. Add update. Now I have to define the shell rebars. Okay, shell rebars. The material name is steel M. I will first define the bars in this direction, parallel to the short side. And the section could be 0.002513. So that's 2,500 square millimeters per meter. It should be the section of 8 bars with a diameter of 20 millimeters. The level is minus 0.07 centimeters, and I will use the normal, which is parallel to the x direction, 1, 0, 0. So if the normal is parallel to this direction, which is the direction of the global axis x, that means the rebars will be parallel to the long direction, perpendicular to the normal. Now I would like to add the bars in the other direction. How do you do that? You just repeat the information given in these boxes with a space at least to separate the information corresponding to the two layers. So I will put 3 spaces. The material is the same. The section in that case would be the same. Could be different, of course. Let's make the level a little bit different. Minus 0.08. The two bars cannot cross each other at the same level. And here, just to have perpendicular direction, I type 0, 0, 0 for the normal. I could type as well 0, 1, 0. That would be the same effect. I'm not using the angle definition because I'm using the normal definition. And add update. And I think I finished all the definitions of the surface. I can make check the material. Okay, it has been defined. The block was defined previously. The load is here. Okay, basically that's it. Now I have to do the mesh. I go in mesh here. And before I do the mesh, I have to define a little bit how the mesh will look like. And I use the transfinite function. I will transfinite the curves. At first, the short supports, I want to have 8 elements along these supports because the length of this support is 4 meters. So that would be 9 points for this line and this line, type E. On the long supports, which are 6 meters long, I want to have 12 elements. That will be 13 points for this line and for this line. And Q. I also have to transfinite the surface to have a structured mesh. I just have to select it once and type E and then Q. I'm now ready to do the mesh 2D. The mesh by GmSAFIR is made of triangles. We know that Saphir wants to have like quadrangles, so we click Recombine 2D. And if we want to improve the visibility, we watch the materials, and here we see all the finite elements which have dimensions of 50 by 50 square centimeters. We are pretty much ready to create the input file. So it's a structural 3D. We will make the name a little bit more clear. Why not concrete slab, which is the same name as the name of the geo file. We use a maximum displacement limit of 1 meter, precision 2, and G beam is not relevant. The time print we will print every 16 seconds, and G shell thick, this is important, we have to change that. 0 would not work, we will use 9. We won't make a dynamic analysis but a static analysis with AP and R, approach Newton-Raphson, which seems to converge a little bit better with the shell finite element. And I come back down to 1 second, and we start with a time step of 1, and it can increase to maximum value of 16. So normally the file should be created, and this is what we see here. So let's go to the folder. The file is here, and without having a look in the file, we are confident that it should run. So we add this input file into Saphir shell and we start running, and Saphir is running. So we will check what the model look like. Okay, the fire resistance time is short because I didn't pay too much attention to the real values that I introduced. That was not the point, to have a long calculation. I come to diamond and I want to open the file here, concrete slab. So here are the nodes, here is the mesh, the supports, and I can see that the supports have been added. For example, in this point, I have the constraint imposed by the long supports and by the long supports. The same here, the same here. And if I move the axis to the corner, I see here on that node, I have all the constraints provided by the short supports, by the long supports, and by the point supports. That's what I wanted. Here are my elements. This is the mesh. Let's remove the supports, the load maybe here. It's okay, it's in the appropriate direction. We can watch the displacements after 16 seconds, and we see that we have a negative displacement, which is what we expected, provided or created by the load, and it will increase slowly with the thermal gradient that appears. And this is the end of this presentation. Thank you.